Hello and welcome to our derivatives mini camp. Over here I have a little postage stamp recognizing Isaac Newton, and you can see it has some planets going around in elliptical orbits. Isaac Newton was one of the original founders of calculus, so it's nice to see him recognized on a postage stamp like that. So in this course we're going to be using material out of this book, Applied Calculus by Denny, Burzynski, great little book, and we're just going to be doing the part in this book that's on derivatives. So I want to welcome you to this class, and also if you're a high school student, you've come out of high school, you're going to be taking calculus in college, and you already had a little calculus in high school, you really want to pay attention to these first few lessons right here because they really tell us the foundations of calculus, what these things are based on, in particular the derivative. So over here, I've got a little diagram. Here's a little function in red here, y is equal to f of x. And if we go any point on the x-axis and then up to the graph, this point right here has coordinates x and f of x. Well, it turns out, depending on what quantities we have, what quantity y is and what quantity f and x is, that the slope of the line tangent to the graph is usually an important number. So not the line itself, but just the slope of the line that's tangent to that graph. That turns out to be a very important number. So how do we find that? We can, adjust that line, that green line, a little bit and see if we can get close to it. But there's a way to do it that's very exact, and it's like this. We go to this number x on the x-axis, and we just move h units farther away from that. So this point on the x-axis is x plus h, this distance x plus this distance h. Then we go up to the curve to this point, and this point now has coordinates x and f of x plus h. That's the height is just f of whatever this number is on the x-axis. So we go to this number, this point right here and this point right here, and we draw a line between them, and that's called the secant line. And we find the slope of that line to begin with. So the slope is just going to be rise over run. So I'll look at it like this. I'll draw this little triangle in. It's a right triangle. This distance here on the triangle is h, and this distance right here is f of x plus h minus f of x. Because it's this height right here, the whole height, minus this height. Well, that height is f of x, that big height is f of x plus h, and so their difference is this height right here. So the slope of that secant line m is equal to f of x plus h minus f of x all divided by h. It's the rise over the run, just this distance right here over this distance. So if we can find the slope of that secant line right there, to find the slope of that tangent line, we just let h move this way on the x-axis, and we keep control of everything with that formula right there. So if I want to find the slope of that tangent line, that m is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And so that formula right there is the derivative of the function y equal f of x. It's the derived function. It's the function that we get when we do this procedure right here to try to find the slope of that line tangent. So that's the derivative. We're going to be doing a lot of work with that in this first lesson right here. And if you're a student just coming out of high school, had a little bit of calculus, now you're going to go on and take calculus in college, you really want to pay attention to this right here because this forms the foundation for what we're going to do with derivatives.